Hello, everyone, and welcome to the Tutor's Guide to AP Calculus. We're going to be talking about the Taylor and MacLaurin series today, and this is basically the big granddaddy topic of Calculus 2, or Calc BC if you're in high school. You do a whole bunch of things all throughout the year, and they all get used here. So you need to know your derivatives in general, and specifically for how I'm going to explain it, you're going to need to know how to do a linear approximation. You're going to need to know how to integrate. And in the end, to make use of all this, you're going to need to know a thing or two about sequences and series. So it's the put it all together topic that is kind of the reason why we have an entire chapter in Calc 2 on sequences and series that seems kind of pointless otherwise. Whether or not you'll actually use the Taylor and MacLaurin series isn't so important because honestly, most people are not going to just randomly bust this out, but it is a very, very important topic in select fields. For example, it is the way that your calculator is going to compute values for sine and cosine, for e to the x, etc., because those are not things that the calculator inherently knows how to do. The way that we make it do that is through the Taylor and MacLaurin series. So what are we doing? Well, we are trying to approximate the value of this point over here, which I've just labeled as x f of x. Now the problem is we don't know what that value is. We don't know what's going on with this function. The only thing we know is what's happening right here at the current moment in time, which is time 0. We know where the function is. We know which way it's going. We know which way it's curving. We know everything about everything at that one point, but we don't know out here. So we're going to have to try to kind of guesstimate. Well, the first most crude way to estimate is to just say, oh, well, it's going to be the same as f0. And you could say, okay, maybe. And in this case, it actually isn't too terribly far off, but that's not too useful. So instead, we're going to do what we did earlier in calculus, and we're going to do a linear approximation. So let's remind ourselves that a linear approximation is basically just a glorified way of doing the point slope formula, which is y minus y1 equals m times x minus x1. So how does this play out in calculus specifically? Well, we know that we're using this point at x equals 0, the y-intercept. So it's y minus f of 0 equals, and it's x minus 0, but we got to talk about the slope. What is the slope of this thing? Well, we really want the slope of the secant line, the line that would extend between here and here, but we don't have that. So we're going to approximate it with a tangent line. Oh, so slope of a tangent line, there's a name for that. We call that, of course, the derivative. So this is going to be f prime at 0. And so there's your function. And if I decide to move the f0 to the other side, we're going to have something like this. Or I guess I could drop the minus 0 part and just write it as f of 0 plus f prime of 0 times x. F of x, because that's what our y value is that we're looking for, right? Okay, so our function value is basically this, but the problem is look at our graph here, right? If I take my tangent line and I do my best to actually make it look like the tangent line at that point, it is nowhere near correct. Well, poop. Okay, so what's the problem? Well, the issue is that the linear approximation is only really good if we stick to really close to the point we're working off of, right? Within that circle, it's not too far off, but once we get out here, we get big old gaps because the function bends away from the line. Bend, bend, bend. What is bend? Bend. There's a word for bend in calculus, isn't there? Oh yeah, it's concavity. So basically, the reason why this is off, because the function has a second derivative. And the second derivative pulls the first derivative away, which in turn pulls the regular function away. So we need to do something about this. It would be nice if we could create, instead of a tangent line, maybe like a tangent parabola. That would account for a second degree, right? Well, maybe we can do that. What if we said, rather than doing a linear approximation on the function, let's pretend that what we were doing was a linear approximation on the derivative. So now what we've got instead is f prime of x is equal to f of 0 plus, or f prime of 0 plus f double prime of 0 times x. Well, okay, great, but we want regular f. How do we get that? Well, seems to me if you want to go from f prime to f, you just do an integral, right? So let's integrate both sides. And if we integrate this expression, we're going to get that f of x is equal to, now f prime of 0 is a constant, and so is f double prime, but we do have times x, so this is times x squared over 2. But this is an indefinite integral, so now we need a plus c. What is the plus c? Well, if we plug in a 0, we can see very clearly that c is going to have to be f of 0. So f of x is equal to, I'm going to move it to the front, f0 plus f prime of 0 times x plus f double prime of 0 times x squared over 2. And if you want to see that without the inline text version, that's f double prime of 0 times x squared over 2. Okay, so let's take a step back and make sure we understand where we got this from. So we did a linear approximation not on the main function, but on the derivative. So this line here is the linear approximation for the derivative. And then to get to the regular function, we integrate using the fundamental theorem of calculus. And what I argue is that if we plug in a 0 everywhere, then these terms go away because they're times 0. And so f of 0 is equal to c. So this is f of 0, and we just brought it to the front. So that's how we got here. All right, well, let's see what our tangent parabola would look like. So we need a parabola at this spot. So it's bending, right? It is bending. It's got some consistent concavity, but it's probably going to do something like this. Oh. Oh, that doesn't work so well, does it? All right, we need to fix this. Why is this not working? Well, the reason why the tangent line, which was based on f prime, didn't work is because there was a second derivative. And the second derivative is making the first derivative change over time. So it meant that our slope was changing over time. Well, our second derivative represents the concavity, and unfortunately the concavity is changing, which means that the concavity has a rate of change. It has a derivative. And if the concavity is the second derivative, then the rate of change of the second derivative is the third derivative. So this is off because the function has a third derivative. All right, well, let's pop back one more level. Let's pretend that the original thing we did the linear approximation for was the second derivative, and this is now the first derivative. So in other words, rather than having done a linear approximation on f of x, we originally said, well, let's do a linear approximation for whatever the derivative function looks like, right? You can do an f to f prime graph and imagine whatever that must look like. Let's do the linear approximation on that, and it wasn't good enough. So now we're going to go one level deeper, and we're going to say, let's do a linear approximation for the second derivative. So what that means, all right, let's think about this piecemeal here, right? It's like f double prime of x equals f double prime of 0 plus f double prime or f triple prime of 0 times x. What I've done is I've taken this line right here, which became this line when we did the first derivative, and I'm saying, let's make this now the second derivative instead. And if we go through all the same processes we just did a second ago, and we integrate this, we get f prime of x is equal to f prime of 0 plus f double prime of 0 times x plus f triple prime of 0 times x squared over 2. All right, confused yet? All I'm doing is I'm saying let's give this thing a name. Let's call it something else's derivative. If this is not clear and this is confusing, either take a second, go back, listen to it, or don't worry about it because the derivation isn't super important. I just kind of want you to have the idea. So if you don't follow the exact math, it's not the end of the world. But we're going to do exactly what we did before. We're going to say, well, we've got f prime, we want f, so let's integrate both sides. And when we integrate this thing, we're going to get f of x is equal to f prime of 0 times x, because that's a constant. This is just some number, so the integral of some number is some number times x, plus, now we've got a regular x here, so f double prime of 0, which is a constant, times 1/2 x squared, plus, all right, and f triple prime is just some number, times the derivative of, or excuse me, the integral of 1/2 x squared is x cubed over 6 plus c. And what we'll realize is that this c is f of 0 for the same reason it was f of 0 before. So, okay, that would create for us a tangent cubic, if you will. So let's guess at what this might look at. Like, I don't actually know what this is going to look like, but let's pretend, for the sake of argument, let's pretend it looks something like this. It won't be perfect, is the point. It's looking a lot better though, right? It's going to get way off out here. Like if I extended this, you'd notice there's a pretty sizable gap way out past where we're looking. And probably the same is true out to the left. But at least within this boundary, it looks moderately accurate. It's coming unfrayed at the point where we're interested in, but it's getting there. So it seems like if we add more terms, it gets more and more accurate. So let's pretend that we just kept going. What the heck would this expression look like? Well, we understand that we have this adding on of terms. Let's look at the progression. We've got the f0 plus f prime x, and then f0 plus f prime of x plus f double prime times x squared over 2. And then we have all that same stuff plus f triple prime times x cubed over 6. So it seems, it would appear that f of x is equal to f of 0 plus f prime of 0 times x plus f double prime of 0 times x squared over 2 plus f triple prime of 0 times x cubed over 6. And then we would add another term if we wanted to keep going. What would the next term be? Well, it would appear that we're having a fourth derivative. So we're going to write a fourth derivative, and that's the notation for how to indicate a fourth derivative, by the way. That does not mean to the fourth power if you put in parentheses. We have an x to the fourth on top, it would seem. How do we go from 2 to 6? let's remember that this is a 1, right? And the way we got the 2 was we integrated. So we did divide by the 2. And then to get to here, we did integrate, so we did divide by the 3. So it means we would divide by 4. So we got 4 times 3 times 2 times 1, or in other words, 4 factorial. Plus dot, dot, dot. And if we kept going, we would have the nth derivative of 0 times x to the n over n factorial. We can extend this fraction all the way if we like. And this right here, this is called the MacLaurin series. This business right here that we did in red. So while it might not be very clear about what we did, this is how we get there. And what this means, let's give a summation here. The significance is that we can write any function as a polynomial. I guess I do need to add one word here, any continuous function as a polynomial, because polynomials are inherently continuous. It probably should say continuous and infinitely differentiable if I'm going to keep adding disclaimers in there. But basically any like normal function, something that's smooth. So we should be able to do this to trig functions, or at least sine and cosine anyway. We should be able to do this to exponential functions and logarithms. We should be able to do this to things like the square root of x, strangely enough, although there is a domain restriction on that. But we should be able to, if we use enough terms, be able to do this. Now you might be saying, well, if I have like an x to the billionth power, isn't that just going to go to infinity? And the answer is, well, yeah, eventually. But because it's divided by like a billion factorial, it has like no bearing until x gets big enough. So I don't have a graphic here for this, but basically if you keep adding on terms, it just kind of makes it get wider and wider and more accurate. The range that we can look at it becomes broader. So, all right, let's actually do one. So let us say that we're going to find the MacLaurin expansion for y equals sine of x. Actually, let's do cosine. I'm going to do cosine because it has a value at 0. So let's rewrite that big long expression. F of x, in this case cosine of x, is equal to f of 0 plus f prime of 0, I'm going to be writing this a lot, times x plus f double prime of 0 times x squared over 2 plus f triple prime of 0 times x cubed over 3, or not 3, 3 factorial. Technically, this is over 0 factorial and over 1 factorial and over 2 factorial. 0 factorial, by the way, we define as equal to 1. It is not equal to some impossible to figure out thing. We define it as being equal to 1. Plus f quad prime of 0 times x to the 4th over 4 factorial plus etc. And hopefully we'll get the idea by the time we get there. All right. So let's make ourselves a little table here. Let's ask ourselves some important questions. So for a given derivative, let's ask ourselves what is the nth derivative at 0 of that value. I guess we only need 2 columns for this. So when n is 0, meaning we're just doing regular old f of 0, oh, I know what I want. I also want to know what is the derivative in general. So this is cosine of x because that's where we're starting from, right? We haven't done a derivative yet. That's why I say n equals 0. Well, regular f of 0 is 1. Okay, well, what if we do the first derivative? Well, now we have negative sine of x, and that's going to give us a value of 0. If I do the second derivative, now we have negative cosine of x, so that's equal to negative 1. 3 is going to give us a 0 because it's going to give us positive sine of x. And when we get to 4, we're going to have a value of 1, which is cosine of x. And it's going to start looping from there, right? So that means then that this is equal to f of 0 over 0 factorial plus f prime of 0 times x over 1 factorial plus f double prime of 0 times x squared over 2 factorial, which is just 2, plus f triple prime of 0 is 0 times x cubed over 6 plus f to the fourth derivative of 0, which is 1 times x to the fourth over 24. Okay, and we would keep going. And what we notice is that, well, this term is 0, and this term is 0 because they're times 0. If we wanted to keep writing terms that weren't 0, it would look like 1 minus, I'll just write as x squared over 2 factorial plus x to the fourth over 4 factorial. And if we had kept going, the x to the fifth term would also be 0 because it would have had the same derivative. The x to the sixth term would have had a negative 1 derivative, so we'll say minus x to the sixth over 6 factorial. X to the seventh would have been 0, x to the eighth would have been 1, so plus x to the eighth over 8 factorial, minus x to the 10th over 10 factorial, plus x to the 12th over 12 factorial, etc. And we're going to keep writing all the even terms, etc. There is a fancy way of writing this if we wanted to kind of sum it up. We would say that this is equal to the sum n equals 0 to infinity of, so we have negative 1 to the n, because we keep alternating signs. However, the first one is, let's see, that works out correctly, okay, times, and then we have x to the 2 times n over 2n factorial. Remember, when we do a summation, it has to count by ones. So if we want to count by twos, we have to take everywhere that we're using that number and double it. So here's our summation notation. We've basically written a really funky way of simplifying the cosine function using the MacLaurin series. I encourage you to try doing this on your own with sine and see what happens. I'll give you a hint, you're going to end up with all the odd powers, but it's going to look otherwise very, very similar. Okay, so that's the MacLaurin series. What's the Taylor series? It's another entire thing. Please tell me that the Taylor series is not complicated. Well, it's not. Taylor series is just the MacLaurin series with a horizontal shift. If I went back to our original situation and I noticed that right up here, I wrote x minus 0. And for 2 steps, I kept it that way before I finally went, okay, let's just call it x. But what happens if instead of working off of a point that was x equals 0, we worked off of some other point here, and we called this c, that was the input value, and this was f of c here. And it turns out that what we do, it all works out exactly the same. So The Taylor series just does what the MacLaurin series does based on a different spot. So it ends up being that f of x is equal to whatever our anchor point is, we're going to call it c, plus f prime of c times, and then it's not times x, but rather x minus c, because we're going to do a horizontal shift, plus f double prime of c times x minus c squared over 2, plus f triple prime of c times x minus c cubed over 6, 3 factorial, plus dot 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 the nth derivative of c times x minus c to the n over n factorial, dot dot dot. And this is useful because sometimes we can't go from 0. Sometimes we have to adjust. We have to go from a slightly different position. So for instance, let's suppose we want to find the Taylor expansion for y equals ln of x centered on x equals 1. And we can't do 0 for ln x because it's undefined. Like, it doesn't even make sense, right? If you recall, ln x basically just looks like this. Oops. And there is no 0 value. So we can't do that. But we can center around 1, and this is actually very fortunate for us because x equals 1 is about the only place that we can just inherently know the value of ln. So I'm going to make our table like we did before. And I'm going to say, what if we are interested in, for a given value of n, what is the nth derivative at 1, or just in general first, and then we'll say at 1. Before we did it at 0, but in this case we're going to do it at 1 because that's what we're centering on. So 0, 1, 2, 3, 4. So, all right, regular old function without doing a derivative is ln of x. ln of 0, ln of 1, excuse me, ln of 1 is 0. It's the x-intercept. All right, derivative of ln x is 1 over x. And you know what? Let's just write out the derivatives while we're at it. Negative 1 over x squared times, because this is x to the negative 2. In fact, let's write it in exponential form just to make it easier to track. So this is x to the negative 1. This is negative 1 x to the negative 2. This is going to be 2 x to the negative 3. We're going to multiply by the power and then drop the power. Just for good measure, I'll write out one more. 24 x to the negative 5th. And if we plug in a 1, well, this is just 1 over 1, 1 over 1, 1 over 1, 1 over 1, 1 over 1. It's just equal to the coefficient. Oh, okay, so we can write that. So ln of x, or f of x, is equal to f of 0, or excuse me, f of 1, our anchor point, our non-differentiated point, plus 1, that's our first derivative, times x minus c, and c is 1, plus f double prime of c is negative 1, so this is a minus 1, times x minus 1 squared over 2 factorial, plus 2 x minus 1 cubed over 3 factorial, minus 6 x minus 1 to the 4th over 4 factorial, etc. Can we simplify this? So we've got x minus 1 minus x minus 1 squared over 2 plus 3 factorial is 6. 2 divided by 6 is 3. So x minus 1 cubed over 3 minus 4 factorial is 24. 6 over 24, we end up with a 4 on the bottom. Over 4 dot dot dot. All right, well, what is the dot dot dot? Well, let's think about it. If we kept going here, the nth derivative here, we would have kept multiplying by the number on top. So we end up with basically an n factorial, right? Except it's not quite n factorial, right? This is 3 factorial, this is 4 factorial, so it's actually off by 1. So what it really is n minus 1 factorial times x to the negative n, which means in turn that our position at 1 is just n minus 1 factorial. So our nth term up here is going to be, there is one other factor to consider, and that is that it's alternating sign. So I guess we have to do times negative 1 to the n. And because the first term that we're working with a value of 1 is positive, I'm going to shift this. Because negative 1 to the n basically just makes it go plus minus plus minus. But we have to make sure that we have it starting in the right spot. So, all right, we got that straightened out. So our nth derivative, if we're going to plug in the general form, is going to be negative 1 n to the n plus 1 times n minus 1 factorial times the regular x minus c to the n that we would have over n factorial. Now, n minus 1 over n factorial. If you didn't know this before, you should have done it with the ratio test a fair bit and recognize that this right here is going to simplify down to just an n on the bottom, because n factorial is n times n minus 1 factorial. And then these cancel. So we have regular old n. So what's the conclusion? ln of x, oh, and x minus c, right, c is 1. So ln of x is equal to negative 1 to the n plus 1. Whoops, I need a summation here. Summation of negative 1 to the n plus 1 times x minus 1 to the n over n. As n goes from, all right, does this work for the 0th term? Let's ask ourselves. If we plug in a 0, we'll end up dividing by 0, first of all, and that's bad. Second of all, negative 1 to the 0, we would have had a 1 here or something like that, and that's not accurate. So in fact, this starts with an n value of 1, not 0. But it works all the way through the rest of the integers. So this right here was our conclusion from all of that work. Yikes. Okay, so I'm basically creating an infinite amount of work for you. That's what seems to be happening, isn't it? That's where this seems to be going. Ugh. Why would we do this? Why? No, that can't be right. All right, well, let's instead do this. Let's go back to our cosine. Cosine of x was equal to 1 minus x squared over 2 plus x to the 4th over 4 factorial, 24, minus x to the 6th over 6 factorial, plus x to the 8th over 8 factorial, etc., 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 dot, dot, dot. Let's see how long it takes to get reasonably accurate, shall we? So we're going to figure out what cosine of 0.1 is equal to. That's 0.1 radians, not 0.1 degrees, mind you. So if you're going to plug that in and check, you should be able to decipher what this is just by typing in cosine of 0.1. But we're going to say 1 minus 0.1 squared over 2. And then let's just leave it at that for the moment. Let's see what that is equal to. 1 minus 0.1 squared over 2. And that gives us 0.995. All right, well, let's add a term to this. So now let's do the x to the 4th version. So I'm just going to take my answer from before and add to it 0.1 to the 4th divided by 24. And I get, oh, you know what? I should, this is 0.995 even. This is 0.995, and I'm going to give you the entire thing on the calculator here, 0.0041667. All right, let's go one more. 1 minus 0.1 squared over 2 plus 0.1 to the 4th over 24 minus 0.1 to the 6th over 720. Don't ask me to do factorials past 6. So minus 0.1 to the 6th divided by 720 is 0.995004163. Look how little this changed. 14 on the very last 2 decimal places. So 14 times 10 to the negative like 7th. It barely did anything. In fact, if we go one more, I'm going to bet, I don't know yet. I'll have to do it and confirm. This is a minus. I'm going to bet you that it's not even going to move the needle. Like, it will be so accurate before that, like, the calculator won't even detect a difference because it doesn't keep enough decimal places. Let's find out. So plus 0.1 to the 8th divided by math 8. Where's the factorial thing? Factorial. Let me make sure that we do this right. Okay, and yes, it's exactly equal to the same thing. It didn't move. So what's the moral of the story? This gets very accurate very quickly, especially for small values being plugged in. And therefore, we only needed 3 terms before we said, good enough. And honestly, if we only cared about accurate to 3 decimal places, we could have stopped right here. Like, the second term was 0.995. The final answer was 0.995004163. So did it really matter that we did extra terms? Not really, no. So because accuracy happens very swiftly, the error margin is actually bounded by the next term. Okay, what in the world do I mean by that? Well, let me highlight everything here and shrink it down just a little bit. So, pardon me, we're going to go like this. Whoop. You get small now. So let's suppose that we wanted to determine cosine of 0.5 accurate to the nearest 10,000th. All right, which position is the 10,000th? Let's think about this. 0.1, 2, 3, 4, 5. So this is the 10th, 100th, 1,000th, 10,000th. Okay, so 4 decimal places. We need this accurate to 4 decimal places. Okay. So we're going to do the same thing we just did, except we're going to use 0.5. So 1 minus 0.5 over 2 plus 0.5, or squared, plus 0.5 to the 4th over 4 factorial. Let's just figure out what this is equal to for starters. No, actually, you know what we're going to do? We're going to make a table. Let's do this with a table. So n, the nth term. So when n is equal to 0, we have 1. When n is equal to 1, we're plugging in a half. So this is negative 0.5 squared over 2, which is equal to negative 0.125, because that's 1/8. I can do that one in my head. When we do 2, it is positive 0.5 to the 4th over 24, which is equal to, let's find out, 0.5 to the 4th divided by 24 is 0.0026. Okay, that's to 4 decimal places. And the next digit is a 0, incidentally. So we're not accurate yet. Let's do 3.5 to the 6th over 6 factorial. So 0.5 to the 6th divided by 6 factorial, which was 720, is, and it writes in scientific notation for me, 0.12345. Fifth digit in was the first one. We have something. All right. What does this mean? This means that because n equals 3 did not affect the estimate, neither will any of the terms after n equals 3. Therefore, because the third term, which is actually the fourth term if we're being technical, but it's the n equals 3th term, because that term is less than 0.001, which was the accuracy we wanted, stopping at n equals 2 is sufficient. We know that our estimate of 1 minus 0.125 plus 0.0026, so our estimate of 0.8776 is guaranteed to be within 0.0000217 of the actual value. This is how estimate and error margin works. In general, with an error margin is always less than the value of the next term, at least when it comes to alternating term sequences like we have here. I guess if you keep adding, what you say is that you are, yeah, well, I mean, this is the way that it's usually expressed. So what we say is that the error margin, the exact error, there's a fancy way we write this, and if you don't feel comfortable with this, don't worry about it. Exact error is equal to the nth term evaluated at x equals, and they use this fancy scripty z thing. It's actually the Greek letter zeta. I'm just going to write a cursive z because I don't know how to write a zeta. Or just basically at that. And so when we come back to our term, which would normally be, you know, f, the nth derivative of c times x minus c. The nth term derivative, I should say. X minus c to the n over n factorial. Turns out that it will be exactly equal to this for this this is zeta thing. If we keep everything else the same, if zeta is between c and the x value we're interested in. Don't worry about the zeta thing. I'm going to tell you right now that unless your teacher makes a big thing out of this, do not worry about the zeta thing. It's confusing and weird. All I want you to recognize is that if you need it to be accurate to within a certain bound, go until you have a term that is smaller than that bound. And the error margin will always tell us that we didn't need to go that far or any farther, basically. And we can stop right there and we will know that it is within this of the exact value. Oh, this was a minus, wasn't it? Not important. Okay, so there is your Taylor, there's your MacLaurin, there's the idea behind it, there's a couple examples, and a very brief talk about the error margin, which I have a feeling we'll have to come back to later, but this is the idea. So this is your guide. Thank you very much.